All right, so now I'm going to show you how to solve some trig equations in which they're asking us to find all the solutions. So not just between 0 and 2 pi, but all solutions. So it looks like we have a quadratic. So we'll go to factor this thing. And as I go to factor this thing, I notice looks like the first and last are perfect squares. So this might be actually a binomial squared. In fact, it is. If we go with 2 cosine x minus 1 and 2 cosine x minus 1, that does work. So that means 2 cosine x minus 1 has to be equal to 0. In order for that to happen, the cosine of x has to be a half. And we know that the cosine of x is a half in the first quadrant at pi over 3, and in the fourth quadrant, at 5 pi over 3. So first quadrant, we have x equals pi over 3. And if we want all solutions, it's going to be pi over 3 plus 2 pi k, so that we can just rotate around and stop at that spot every time. In the fourth quadrant, it's going to be x equals 5 pi over 3 plus 2 pi k. And so that is how you write the solutions when they ask for all the solutions from negative infinity to infinity. Now for this one, when you have something in the first and the fourth quadrant like we do here, you could combine it into one statement and say x equals plus or minus pi over 3, because I'm going pi over 3 in the positive direction, but I also can have a negative pi over 3 is the same thing as the same coterminal angle as 5 pi over 3. So plus or minus pi over 3 plus 2 pi k. So that's also a solution. So let's jump to next to number 58. And in 58, we're going to do, again, it looks like we can factor this thing. So we'll set up our two binomials. This will be 2 sine of x times the sine of x. Gives me 2 sine squared. And these are pretty easy factors because you only have one choice. It's 1 and 1. And everything's going to be positive, so it works out. Adds up to 3 sine x in the middle. So we're going to set 2 sine x plus 1 equal to 0, and the sine of x plus 1 equals 0. Here, the sine of x has to equal negative a half. And then the other factor, the sine of x, would have to equal negative 1. So if we just go between 0 and 2 pi, we know that in the sine of x equals negative a half, that's going to be in the third and fourth quadrant. So in the third quadrant, we would have x equal to 7 pi over 6, and then we'd add 2 pi k to it. In the fourth quadrant, we could say negative pi over 6, or we can say 11 pi over 6, doesn't really matter, plus 2 pi k, either one is correct. Since they didn't restrict us to be between 0 and 2 pi, I could have said negative pi over 6. If we're over here for the sine of x equals negative 1, that's only going to happen one time, and that's when x is equal to either, well, you could say 3 pi over 2, or we could also say negative pi over 2, whichever you prefer, but we do have to add 2 pi k to it either way. So there are some options here that you have, but these are my answers that we would get for all solutions. So number 59 is next. Let's take a look at that one. This one is not a trinomial, but we notice there's a sign in both terms, so we can factor out a sine of theta. We're left with a sine of theta minus 2 equals 0, which means the sine of theta has to equal 0, or the sine of theta minus 2 has to equal 0. For the sine of theta equals 0, that means theta is going to be either 0 or pi, and that's between 0 and, just around the unit circle once. And for the sine of theta minus 2 equals 0, the sine of theta has to equal 2, and that is impossible. The sine of theta cannot equal 2 because the sine of theta can only be between negative 1 and 1. So my answers are theta is going to be, I can say 0 plus and minus 2 pi k, and pi plus or minus 2 pi k, but the easiest thing to do is just to say 0 plus pi k, because that's going to take me from here to here, and if I add another pi, it's going to take me here. So I don't really need to write both of them down. In fact, I can just write theta equals pi k, would be the simplest way for me to write that. All right. I think that should give you a pretty good idea of how to do these problems, so I'm going to stop.